Here we have a sequences question from the Leave Insert Ordinary Level Maths exam. So press pause and try A, B, where you complete the table. And then when you've tried those, move on to the next slide where you'll see the next few questions. So the next few questions are C, D, E, F, G and H. So again, press pause and try these questions, and then when you're ready for the solutions, press play. Okay, so the first three patterns in a sequence of patterns are shown below. So here we have term 1, which is 3 black triangles and 1 white triangle. Term 2, which is 1, 2, 3, 4, 5, 6 black triangles and 1, 2, 3 white triangles. Then we have term 3, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 black triangles and 1, 2, 3, 4, 5, 6 white triangles. Part A, draw the fourth pattern in the sequence. So basically what comes next after this third term. So here we have the fourth term in our sequence. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 black triangles and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 white triangles. So how did we come up with this? Well, if you notice in the first term, we've got 2 black triangles on the bottom and then 1 on top. In the next term, we have 1, 2, 3 on the bottom, then 2 and then 1. Just focusing on the black triangles for now. Then in the third term, we have 4 black on the bottom, then 3, then 2, then 1. So next we're going to have 5 black triangles on the bottom. Then 4, then 3, then 2, then 1. Part B, complete the table below. So in the first pattern, the number of black triangles is 3. So we have 1, 2, 3 black triangles in the first term. And we have 1 white triangles. The number of white triangles is 1 in the first term. And then the total number of small triangles is 3 plus 1, which equals 4. So T1, the total number is 4. So 1, 2, 3, 4 triangles. So now we have to fill in the rest of the table. So we have to look at pattern 2 or term 2 and write in how many black triangles, how many white triangles, and then add them up. Then we have a look at term 3, look at the black triangles, the white triangles, then add them up. Pattern 4, the number of black triangles, the number of white triangles, add them up. And then pattern 5, the number of black triangles, the number of white triangles, and add them up. So we wouldn't have actually drawn out pattern 5, but hopefully by the time you've filled in the rest of the table, you can see what's happening with the numbers. So here we have term 2. We can see there's 1, 2, 3, 4, 5, 6 black triangles and 1, 2, 3 white triangles, and 6 plus 3 makes 9. Then in the third term we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 black triangles and then 1, 2, 3, 4, 5, 6 white triangles, and 10 plus 6 makes 16 small triangles all together in term 2. So now we have term 4, so this is the pattern that we had to draw ourselves. So black triangles, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 black triangles. And then white triangles, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 white triangles. And 15 plus 10 makes 25 small triangles in total. So we did not draw out pattern 5. We could do if we wanted to. But we could also just have a look at the numbers and see what's happening to them. So the number of black triangles started off with 3 and then it went to 6. So we started off with 3 and then we added on the extra 3 to make 6. So we added on these 3 here at the bottom to make the 6. And then for pattern 3, where we had 10 black triangles altogether, we started with the 6 and then we added on 4 to make 10. So we started with the 6, which is basically what we have at the top here, and then we added on these extra 4 to make 10. So then for the fourth pattern, we started with the 10 and then we added on 5 more black triangles to make 15. So we had the 10 and then we added on these 5 at the bottom here to make 15. So hopefully you can start to see a pattern. We started with 3, then we added on 3, then 4, then 5. So next we're going to add on 6. So to the 15 that we already had in term 4, we add on another 6, so it will be a row of 6 at the very bottom, a row of 6 underneath these 5, and 15 plus 6 would make 21. So in the next pattern after this one, we'd have 21 black triangles. And then if you wanted the next one after that, let's say pattern number 6, you'd add on 7 to the 21. And if you wanted the next one, you'd add on 8. And if you wanted the next one, you'd add on 9, and so on. So now let's have a look at the number of white triangles. So in the first term, there was 1 white triangle. And then in the second term, we can see there was 3. And 1 plus 2 makes 3. In the next term, there were 6. So we had the original 3 from term 2. Then we added on 3 to make 6. So we had the original 3 from term 2, which is basically those 3 there. And then we added on 3 to make 6 altogether. So then we had 6 in pattern 3. And then for pattern 4, we ended up with 10 white triangles because we had the original 6 and then we added on 4 to make 10. So we had the original 6 and then we added on the 4 white ones to make 10. So again, we did not actually have pattern 5 drawn out, but hopefully you can start to see what's happening here. So we started off with 1 white triangle in term 1, then we added on 2, then 3, then 4. So we're going to add on 5 to the 10 to make 15 for the next pattern. So we'd have 10 white triangles all together in the fourth pattern. And if we added on another 5 at the bottom, we would have 10 plus 5 would make 15 white triangles. So if we wanted the next one, we'd add on 6. If we wanted the next one, we'd add on 7. If we wanted the next one, we'd add on 8, and so on. And then 21 plus 15 makes 36. So 36 small triangles in total. Now have a look at these numbers: 4, 9, 16, 25, 36. Hopefully you'll recognize these numbers as special numbers that we've learned. So we'll have a look at them again in a minute. Part C. Show that the number of black triangles forms a quadratic sequence. So here we have the number of black triangles: 3, 6, 10, 15 and 21. And we want to show that these form a quadratic sequence. So a quadratic sequence is when the second difference is the same. A linear or an arithmetic sequence is when the first difference is the same. So we want to show that the second difference between these numbers is the same, because we want to show that they're quadratic. So here I've written them out in a list. So 3, 6, 10, 15, 21, 3, 6, 10, 15, 21, ... So let's have a look at the first difference. We're going to check the first difference. To get from 3 to 6, we add on 3. To get from 6 to 10, we add on 4. To get from 10 to 15, we add on 5. And to get from 15 to 21, we add on 6. So we can see that this first difference is not the same, so therefore this pattern is definitely not arithmetic or linear. So if all these numbers were the same in green here, it would be an arithmetic or a linear sequence, but they're not. So next we check the second difference. So to get from 3 to 4 we add 1, to get from 4 to 5 we add 1, to get from 5 to 6 we add 1. So we have the same number, a constant. So since it has the same number, it is quadratic. So it doesn't matter what this number is. It could be 2, 2, 2. It could be 10, 10, 10. In this case, it's 1, 1, 1. It doesn't matter what it is so long as it's the same. Therefore, we have a quadratic sequence. So if we were to draw this out on a graph, it would either be U-shaped or N-shaped, because a quadratic sequence will always form a U or an N shape. Part D. 1. How many black triangles in the ninth pattern? How many white triangles in the ninth pattern? And how many small triangles in total in the ninth pattern? So we end up getting 55 black triangles in the ninth pattern, 45 white triangles in the ninth pattern, and adding these together, 55 plus 45 is 100 small triangles in total in the ninth pattern. So let's have a look at where these numbers came from. So this was our original table that was given to us in the question. So on a separate page, or just at the bottom if you had space, you could have drawn out a few extra rows. So this was the fifth pattern. So underneath it we've got the sixth, then the seventh, then the eighth, and then the ninth, which is what we're interested in. So we noticed a pattern inside of our pattern. We noticed that for the number of black triangles, we started off with 3, then we added on 3 to get 6, then added on 4 to get 10, then added on 5 to get 15, then added on 6 to get 21. So now we're going to add on 7 to get 28, add on 8 to get 36, add on 9 to get 45, and add on 10 to get 55. So we went 3, 4, 5, 6, 7, 8, 9, 10. So in the ninth pattern, there's 55 black triangles. Then for the white triangles, we started with 1 white triangle in the first term. We added on 2 to get 3, added on 3 to get 6, added on 4 to get 10, added on 5 to get 15. So then we're going to add on 6 to get 21, add on 7 to get 28, add on 8 to get 36, and add on 9 to get 45. So we went 2, 3, 4, 5, 6, 7, 8, and 9. So there's 45 white triangles in the ninth pattern. And then for the total, well, we just have to say 55 plus 45 is 100. But I've done out the working out for the rest of them as well. So 28 plus 21 is 49. 36 plus 28 is 64. 45 plus 36 is 81. And 55 plus 45 is 100. So earlier on I said to you, have a look at these numbers here and see, do you recognise them? They're special numbers. 4, 9, 16, 25, 36. And now we also have 49, 64, 81 and 100. Well, these numbers are the square numbers. So 2 squared is 4, 2 times 2 is 4. 3 squared is 9, 3 times 3 is 9. 4 squared is 16, 4 by 4 is 16. 5 squared is 25, 5 by 5 is 25. 6 squared is 36, 6 by 6 is 36. 7 squared is 49, 7 by 7 is 49. 8 squared is 64, 8 by 8 is 64. 9 squared is 81, 9 by 9 is 81. And 10 squared is 100, 10 by 10 is 100. Part E. Write an expression in n for the total number of triangles in the nth pattern. So this is a complicated way of saying come up with a formula for the nth pattern, or come up with a general rule for the nth pattern. So write an expression in n, that means in terms of n, so you want to have n in your answer. So that means with the table that we looked at a minute ago, focus in on these numbers here, our square number sequence. We're going to write them out again. 4, 9, 16, 25, 36, 49, 64, 81, 100. We're going to write this out again and try and come up with a formula or a general rule to describe this sequence. So here we have our sequence again, 4, 9, 16, 25, 36, 49, ... Now, we know that n squared, our square number sequence, is actually 1, 4, 9, 16, 25, 36. So it's very, very similar to what we've got, but it starts with a 1, because 1 squared is 1. So our square number sequence, n squared, is 1, 4, 9, 16, 25, 36, and so on. So it's very, very similar to the sequence that we are given. The only difference is we're starting with 1, whereas that sequence starts with 4. So our triangle sequence is the same as n squared. So our sequence at the top is the same as n squared underneath it, but it starts at 4 and not 1. So our sequence starts at 4, whereas the actual n squared sequence starts at 1. So it starts one step forward compared to n squared. Therefore, our nth term is n plus 1 squared. So it starts one step forward, so it's n plus 1. So Tn, the nth pattern, is n plus 1 squared. Part F. The number of black triangles in the nth pattern is given by the formula Bn equals a half n squared plus 3 over 2n plus c. Find the value of c. So we have to find what this number represents. This c here, what does that actually represent? So we're given Bn equal to a half n squared plus 3 over 2n plus c. So this is the nth pattern, or the formula for the number of black triangles. So what we're going to do is have a look at term 1. So here we have term 1 again. And in term 1, we can see that there are 1, 2, 3 black triangles. So if we swap this n, which represents the term number, for 1, and we do the same with all the n's, so we swap this n for 1 with brackets, that's important, you have to use brackets, and we swap this n for 1 with brackets. And then what we're going to do is let it all equal to 3 in the next step, because there are 3 black triangles in term 1. So a half times 1 squared, well 1 squared is 1, and 1 times a half is just a half. Or you can just put this straight into the calculator and get a half. 3 over 2 multiplied by 1 is 3 over 2, because anything multiplied by 1 is just itself. And we still have the plus c, and now this is equal to 3, because there are 1, 2, 3 black triangles in pattern 1. Then a half plus 3 over 2 is 4 over 2, so 1 plus 3 is 4, so 4 over 2. We still have the plus c, and we still have the equals 3. And 4 divided by 2 is 2. So we have 2 plus c is equal to 3. We want to find the value of c. That basically means solve for c. So we minus 2 to both sides, or you could say you bring this 2 over the equal sign and becomes minus 2. And 3 take by 2 is 1. So c is equal to 1. So in this formula, we are asked to find the value of c, and c is 1. Part G. Use your answers to part E and F above to find a formula for the number of white triangles in the nth pattern. So in part E, we came up with Tn equal to n plus 1 squared. So this is the nth term for the total number of triangles. In part F, we came up with Bn, well, we were actually given this, we just came up with the 1 ourselves. So we were given Bn equals a half n squared plus 3 over 2n plus c, and we worked out that plus c to be plus 1. So this is the nth term for the number of black triangles. Now we know that if we add together the black and the white triangles, we get the total number of triangles. So we can reword that and say, well, the number of white triangles is the total number of triangles minus the number of black triangles. So if the white triangles plus the black triangles give us the total number of triangles, then the white triangles is therefore equal to the total number of triangles minus the black number of triangles. So the formula for the total number of triangles is n plus 1 squared, so that's here, we got that in part E. And the formula for the black triangles is a half n squared plus 3 over 2 n plus 1, which we got from part F. So this minus this will give us the formula for the number of white triangles. So we're going to start by multiplying out the brackets. N plus 1 squared. Well, that's the same thing as n plus 1 multiplied by n plus 1. So this is our rough work. So I'm just going to zoom in on this for a second. So it's going to be n plus 1 squared, which is n plus 1 times n plus 1. So we're going to crack open the first egg, and we're going to bring down the n, and we're going to stick it onto the second egg, which we didn't crack open, so we stick it onto n plus 1, and then we bring down the plus 1, and again we stick that onto the second egg again, which is the n plus 1. Then we multiply out the brackets. N multiplied by n is n squared, n multiplied by 1 is 1n, or just n. 1 multiplied by n, again, is 1n, or just n. I'm actually going to stick in the 1s, because it's no harm to see them. And then 1 multiplied by 1 is 1. You'll be careful, don't add. Don't say 1 plus 1 makes 2. We're multiplying. Brackets mean multiply. 1 multiplied by 1 is 1. Then we bring down the n squared, and 1n plus 1n is 2n, and then we bring down the plus 1. So this became this. So n plus 1 squared, we got to be n squared plus 2n plus 1. So we have n squared plus 2n plus 1. Then we had a minus, and in brackets we had our formula for the black triangles, which we got up here. We got that in part F. So now what we have to do is multiply in this minus. So a minus times a half n squared is minus a half n squared. We just stick them together. A minus times plus 3 over 2n is minus 3 over 2n. And a minus times plus 1 is minus 1. So we have n squared plus 2n minus 1 minus a half n squared minus 3 over 2n minus 1. And don't let the fractions throw you off, because it is just simplifying. So the plus 1 and the minus 1 we can just cancel out. So 1 take away 1 is 0, so we can just get rid of them. We're not going to have 1s in our answer. Then we put the squareds together. So this is n squared. So this is actually 1n squared. An n squared on its own is really 1n squared. And 1n squared minus a half n squared is a half n squared. So if you're unsure with your fractions, you can just put into the calculator 1 minus a half, and you'll get a half. And then you just stick on the n squared. The power does not change because we're adding and subtracting. Whenever we're adding and subtracting in algebra, we do not change the powers. We only ever change the powers when we're multiplying or dividing. So then we put the n's together. So we have 2n minus 3 over 2n is a half n. So again, if you're unsure with your fractions, you put into the calculator 2 minus 3 over 2, and you'll get a half. And then you just stick on the n. And the n does not change. It doesn't become n squared or n cubed or anything like that. It stays as n because we were just adding and subtracting. So our answer for a formula for the white triangle's nth term is a half n squared plus a half n. Part H. One particular pattern has a total of 625 triangles. Find the number of black triangles and the number of white triangles in that pattern. So what we're going to do is let the total triangle's nth term equal 625. So this is a formula that we already came up with, and we're going to let it equal 625 and then solve for n. So the total triangle's formula or pattern, nth term pattern, is n plus 1 squared. So we worked this out already. We're going to let this equal 625 and then solve for n. So solve for n means get the n on its own. So the first thing we have to do is get rid of this squared. So we can square root both sides because that's the opposite or the inverse of squared. So square rooting the left hand side, we'll just cancel out that squared. And then square rooting the right hand side, the square root of 625 is 25. So the opposite of squared, x squared, is square root. So another way to do this is just to say, well, we've got squared on this side, so we bring it over the equal sign and it becomes the opposite, which is the square root. So n plus 1, so we just bring down this n plus 1, because remember we got rid of the brackets and the squared. N plus 1 is equal to 25, because the square root of 625 is 25, because 25 times 25 is 625. And then we have to get the n on its own. So one way is by minusing 1 from both sides to get rid of this plus 1. Or you could say you grab hold of this plus 1, you bring it over the equal sign and it becomes minus 1. So 25 minus 1 is 24, so n is equal to 24. So in the 24th term, we have a total of 625 triangles. So we want to find the number of black triangles in the 24th term, or the 24th pattern, and we want to find the number of white triangles also in the 24th term, or the 24th pattern. So to do that, we substitute n equal to 24 into the black nth term formula and into the white nth term formula. So we're going to substitute n equals 24 into the black triangle nth term and into the white triangle nth term. So here's the white one. So this is the one that we came up with ourselves. So the white triangle's nth term is equal to a half n squared plus a half n. So we swap each of those n's for 24, but make sure you put brackets around it, or else it'll go all wrong. So a half times 24 squared gives us 288. And a half times 24, a half of 24 is 12. And 288 plus 12 is 300. So you could have just put this into the calculator all in one go, but it is important to see where it comes from. So we get 300 white triangles. Then we have our black triangle nth term formula. So that is a half n squared plus 3 over 2n plus 1. So we were given most of this formula. We were just not given the 1 at the end. This was actually given to us as a plus c. So a half n squared plus 3 over 2n plus 1. So again, we swap each of those n's for 24, but we must put brackets around the 24. So a half times 24 squared is 288. And 3 over 2 times 24 is 36. And adding on 1. So 288 plus 36 plus 1 is 325 black triangles. So we could have just put this into the calculator altogether, but it is important to see where it comes from. So we get 325 black triangles. So in the 24th term, there's 300 white triangles and 325 black triangles, and adding these together, 300 plus 325 gives us 625 in the total.